Question 5 is about waves, and it starts off with standing waves on a guitar. So, on a guitar, the strings played vibrate between two fixed points. The frequency of the vibration is changed, by changing the string length using a finger. The different strings have different wave speeds. When a string is plucked, a standing wave forms between the bridge and the finger. Outline how a standing wave is produced on the string. Okay, and that's worth 2 marks. So we need 2 points here. Now, this is often a very common question, and you really do need to know the definition of how, or be able to describe how a standing wave is produced. It will come up quite often in exams, and you don't want to be caught out by this. So I'm just going to write down the first thing that happens. So we get a wave, and it moves along the length of the string, for example, and then reflects. Okay, so we have a wave that moves along and then reflects. So that's the first step. The second thing is, now we've got a wave that's incident, that's passing in one direction, and then we have a reflected wave that's passing kind of towards the incident wave. So we get interference of the incident and reflected waves, and it's good to call them incident and reflected. So you could call this either superposition or interference. It's superposition, all one word. It is not superimposition. Okay, it's superposition. Okay, or interference of the incident and reflected waves. There is a third point that you can write. It's not often written by students, but I do see it from time to time. It's the idea that the superposition is reinforced, occurs, is reinforced only for certain wavelengths. Okay, so you will have seen this when we're using a signal generator and a vibration generator. So you'll see that if you've got like a string like that and you're sending waves like that from a vibration generator, so when your teacher's done that and then they come back, you don't always get that beautiful standing wave. So it only occurs for certain wavelengths, certain frequencies, and if the frequency isn't right, then you're not going to get this beautiful standing wave. Okay, you just get kind of, it looks a bit like a muddle. That's what that means. 5b, it's asking for the speed of a wave when it's a standing wave. So we know that the speed of a wave equals v equals f lambda. So speed equals frequency times by the wavelength. We're not actually given the wavelength, but by utilizing the information in the question, we can determine it. So we know that it's in its first harmonic. And because it's a string on a guitar, it's being held down by the finger there, and then the end of the string is there at the bridge. So it's in its first harmonic, and the first harmonic looks like this. These are patterns you need to know. So the string is a length here. The length is 0.62 meters. I'm going to convert to meters. And we've actually got half a wavelength here. You can see that if I was to continue the wave, I'll do it backwards because I've got more space. like that, we can see that the red and the blue equals the shape of a full wavelength. So I've got half a wavelength here. Okay. So if 0.62 equals half a wavelength, therefore one wavelength equals 2 lots of 0.62, which equals 1.24 meters. So V equals 195 times 1.24, and so the speed is 242 meters per second. And I think I'm going to keep it in 3 sig figs because it's saying a show that again, so we need to go to more than 2 sig figs. So it needs to be at least 3 sig figs. Notice we didn't use this value, okay, but that's okay. It's just setting off a little alarm bell that we're going to most likely need it later on in the question. Sketch a graph to show how the acceleration of the point P varies with its displacement from the rest position. Right, okay, now we're going to need that 0.4. Let me just go back up to it. It says the string is displaced 0.4 centimeters at point P. So the displacement, we're going to go up to from 0 to 0.4 centimeters. So I'm going to put this in centimeters. So I'm going to put, let's put 0.4 here. And I could go to negative 0.4 here. Now, interestingly, the mark scheme doesn't ask for that value on the graph. I'm not sure why, because a sketch normally needs to have the important data on it, but it doesn't need a full scale. Okay, and also in the question it did give us that value 0.4. So I must be honest, I was expecting the mark scheme to require the 0.4, but it doesn't actually talk about numbers. It's just talking about the shape of the graph. So how do we know what shape of the graph it is? If you look in the data booklet under waves, you will notice that A is proportional to minus x, and that means acceleration is proportional to negative displacement. So in other words, we're going to have a negative gradient and this is a straight line. So I won't be able to do a straight line on my screen, but it needs to go through 0. Okay, it must go through 0, and we're looking for a straight line, and I'm going to start it at minus 0.4, and I'm going to end it at 0.4. As I say, this isn't going to be straight. You would be expected to do this with a ruler and ideally a pencil